Welcome to ThirdEye Labs, where we make the unseen seen. Part 3. The symbols that separate casual readers from fluent ones. The Gaussian, Variance, the ELBO. By the end, you will read research papers like a native speaker. The curly N is not just another symbol. It is the symbol. The Gaussian, or normal distribution, the bell curve. Mu is the center, where the peak sits. Sigma squared is the variance, how wide the bell spreads. Nearly everything in machine learning assumes data follows this shape. Neural network weights, noise in images, even the errors we try to minimize, all Gaussian. Think of the heights of everyone in a city. Most people cluster near the average. Very few are extremely tall or extremely short. Draw that as a graph and you get the bell shape. That is the Gaussian hiding in a crowd. Variance measures spread. How far do the values scatter from the mean? It is just the average of the squared distances. Covariance asks a different question. Do two variables move together? If x goes up when y goes up, covariance is positive. If they move opposite ways, it is negative. Zero means they are independent. In real life, ice cream sales and sunburns rise and fall together. That is positive covariance. Neither one causes the other. They both just follow the sun. Covariance measures that shared movement, not the cause. The vertical bar is one of the most powerful symbols in all of probability. P of x given z. The probability of x if we already know z. Bayes' rule lets us flip that condition. If we know P of x given z, we can compute P of z given x. The proportional symbol means we can ignore the normalizing constant. This is the engine of every generative model. It is just like a detective. You start with a hunch, a prior belief. Then a clue arrives, the evidence, and you update how sure you are. Bayes' rule is simply doing that update with numbers. Bayes' rule sounds abstract, so let us see it as a picture. Here are 100 people. A disease affects just one of them. Now we run a test that is 99% accurate. The one sick person tests positive, in red. But the test also makes mistakes on healthy people. About 5 healthy people are wrongly flagged as positive, in yellow. Watch what that does. Here is the shock. 6 people tested positive, but only one is truly sick. So if you test positive, your real chance of being sick is just 1 in 6. About 17%. Not 99. The rare disease stays rare, even after a positive test. And this is exactly what Bayes' rule computes. The prior is how rare the disease is, our single red dot. The likelihood is the test's accuracy. The bottom, the evidence, is everyone who tested positive, red, and yellow together. Divide, and you get that 17%. The formula was never abstract. It was counting dots all along. This is why a good doctor never trusts a single positive for a rare disease. They run a second test. Because, as the dots showed, one positive on something rare is usually a false alarm. 2 final connectors you will see in every probability paper. The squiggle, the tilde, between a variable and a distribution means, is drawn from. X tilde normal mu sigma squared reads, X is sampled from a Gaussian. And the stretched-out proportional sign means equal, except for a constant factor. It is why Bayes' rule is often written as, the posterior is proportional to the likelihood times the prior. We simply drop the normalizing constant, because it does not change where the peak is. The tilde is like saying a roll comes from a fair die. And proportional to is like comparing prices before tax. The exact numbers shift, but the ranking, which is cheapest, which is most likely, stays the same. The blackboard bold I with brackets is the indicator function. It is a simple switch. 1 if the condition is true, 0 otherwise. This lets us count things inside a sum. For example, this line counts how many data points have label C. The indicator turns logic into arithmetic. Picture a bouncer at a club door. Meet the condition, he counts you as a 1. Fail it, you are a 0. At the end of the night, adding up his clicks tells him the size of the crowd. The indicator is that bouncer. A tiny detail that unlocks so many equations, the small print written under a symbol. It tells you what the operator is acting on. Under the expectation, x drawn from p means average over that distribution. Under nabla, theta means take the gradient with respect to theta and nothing else. Under argmin, theta means search over theta for the smallest value. The big symbol tells you the action. The subscript tells you over what. Always read the subscript. It is like a recipe that says stir over low heat. The verb stir is the action. The small print over low heat tells you the exact condition. A subscript is that small print. Skip it and you burn the sauce. Tan, hyperbolic tangent, looks like sigmoid but centered. It squashes inputs to -1 to +1. LSTM use tan to control what information flows through the gates. The symmetry around 0 helps gradients flow better than sigmoid. Think of a steering wheel resting at 0. Turn it left for negative, right for positive, and straight ahead means no change. Because tan is centered at 0, it steers both ways evenly. That balance helps a network learn. BatchNorm and LayerNorm look identical, but they normalize different axes. BatchNorm takes the mean and variance across the batch. LayerNorm does it across the features, for each example separately. Transformers use LayerNorm because it works with variable batch sizes. Both subtract the mean, divide by standard deviation, then scale and shift. That is what keeps gradients healthy during training. It is like grading an exam on a curve. Subtract the class average, divide by how spread out the scores are, and suddenly every test is on the same scale. Normalization does exactly that to the numbers inside a network. 4 operations that appear in every linear algebra-heavy paper. Transpose flips rows into columns. You see it in dot products, x transpose y. Inverse undoes a matrix. A times a inverse equals identity. Trace sums the diagonal. It shows up in eigenvalue equations. And diag turns a vector into a diagonal matrix, off-diagonal all zeros. Transpose is just flipping a spreadsheet, so the rows become columns. And the trace is even simpler. You just add up the numbers running down the main diagonal. 2 scary words, 2 everyday moves. 2 very different multiplications hide behind similar-looking symbols. The circle with a dot, called Hadamard or element-wise, just multiplies matching positions. 2 times 4 is 8, 3 times 5 is 15. The shape stays the same. But plain matrix multiplication is the row dotted with column rule, and it mixes everything together. 1 times 5 plus 2 times 6 is 17. Mixing these two up is one of the most common bugs in all of deep learning. The little circle is your warning sign. Element-wise is like 2 lines of people shaking hands, 1-to-1, neat and matched. Matrix multiply is a big committee where everyone talks to everyone before a single answer comes out. Very different rooms. Fancy curly letters, calligraphic script mark abstract concepts. Curly D is the dataset, all your training examples. Curly L is the loss function, what you are trying to minimize. Curly H is the hypothesis space, the set of all models you could pick. And curly P is a probability distribution, often a prior in Bayesian methods. When you see calligraphy, think sets, spaces, families of functions. Think of a library catalog. A fancy letter does not name a single book. It names the whole shelf, an entire family or space of things. So when you see calligraphy, think collection, not item. Here is a symbol that means 3 different things, and it confuses everyone. Vertical bars. Around a number, single bars mean absolute value. The size, ignoring the sign. Bars of -3 are 3. Around a set, they mean its size, the count of items. The set A, B, C has size 3. But double bars around a vector mean its length, the norm we met earlier. Single bars, a number or a set. Double bars, a vector. Now you will never mix them up. It is like the word bat. The very same letters mean a flying animal or a piece of sports equipment. Only the context tells you which. Vertical bars are exactly that. The shape stays the same, The context decides the meaning. The ELBO, evidence lower bound. This single line is the foundation of variational autoencoders. The first term is reconstruction. Given latent code Z, how well can we recreate X? The second term is regularization, KL divergence. It keeps the learned distribution Q of Z close to the prior, usually a Gaussian. Maximizing this lower bound trains the entire V a E. One equation, two forces, generative modeling. It is like describing a photo to a friend over the phone. You want to be accurate enough that they can recreate it, but simple enough that you can actually say it out loud. The ELBO balances those exact two pressures. Last two quick ones. Floor and ceiling. Floor rounds down. 3.7 becomes 3. Ceiling rounds up. 3.2 becomes 4. You see these when papers compute how many batches fit in an epoch, or when they quantize continuous values into discrete bins. Real life. You cannot buy 2.3 movie tickets. The ceiling rounds you up to 3, what you must pay for. The floor rounds you down to 2, like the whole dollars you actually keep. Same number, two honest roundings. Let us recap the complete vocabulary. The Gaussian, curly N, the bell curve that governs almost everything in machine learning. Variance and covariance measure spread and co-movement. Conditional probability and Bayes' rule let us flip conditions. The indicator function turns logic into arithmetic. Tanh, BatchNorm, and LayerNorm are the operations inside every network. Transpose, trace, and inverse are the matrix operations you see everywhere. Calligraphic letters mark abstract spaces and families of functions. And the ELBO is the objective that trains variational autoencoders. Across 3 parts, we covered the entire language. Part 1 gave you the alphabet. Part 2 taught you to read full sentences. And Part 3 unlocked the deepest symbols, the ones that separate casual readers from fluent ones. You can now read research papers like a native speaker. Thanks for watching, and keep exploring. Next time, we begin Season 1, the language of I itself, linear algebra, where a matrix becomes a transformation of space. Please like and subscribe ThirdEye Labs if you enjoyed this trilogy, and let me know in the comments which paper you want me to break down next.